Welcome to Talk Tensors. So, usually when we talk about software engineering, there is this ingrained expectation of clean modularity.
Right, the whole Lego brick philosophy.
Exactly. We expect things to just work like Lego bricks. You build a microservice for, say, user authentication. You build another completely separate one for image processing.
And when it's time to deploy, you just snap them together.
Yeah, the process is additive. It's totally predictable. But then you step into the world of modern machine learning, specifically with these massive, heavily parameterized neural networks. And suddenly you realize those Lego bricks are, they're actually made of wet clay.
That is a highly accurate way to put it.
Because you try to smash two highly capable models together, right? You want the best of both worlds. And instead of getting this amazing supermodel, you get a gray, muddy mess that has just completely forgotten how to do either task.
Which is the absolute definition of catastrophic interference. I mean, we naturally want to think of knowledge as cumulative,
Right, like human learning.
Exactly. If you read a book on biology and then a book on history, you now know both. But in the high-dimensional parameter space of a neural network, adding new knowledge is often, actively destructive to existing knowledge.
And that destruction, that fundamental incompatibility, is exactly what we are tackling today. On this deep dive, we are covering a massive viral breakthrough in machine learning that is just dominating developer timelines right now.
It really is everywhere right now.
Oh, absolutely. It's a radically new architecture for what's called model merging. And if you're a practitioner, a researcher, or just, insanely curious about where AI is heading, the absolute headache of the current deployment paradigm.
Oh, the deployment side is a nightmare.
Right. So imagine you're running a sauce platform. You have a massive pre-trained foundation model, but your customers need it to do 10 very different things.
Like what specifically?
Well, they need sentiment analysis, they need Python code generation, maybe they need legal document summarization, and I don't know, some image captioning.
All very distinct tasks.
Very distinct. And right now, to get state-of-the-art performance, you are probably juggling dozens of specialized, fine-tuned models.
Yeah, and the overhead for that is just entirely unsustainable at scale. I mean, think about the VRAM constraints alone.
It's brutal.
You are essentially paying exorbitant cloud computing rent on an entire skyscraper when you only really need to use one room on each floor.
Which perfectly brings us to our mission for today's deep dive. We're going to unpack a trending technology that completely bypasses this problem.
A total workaround.
Exactly. We're looking at a method that combines multiple task-specific AI models into one giant, highly capable multitask model. And the crazy part, it does it absolutely without any expensive retraining.
Not at all.
So we're going to cover why this specific bottleneck matters right now, break down the brilliant three-step architecture of, how the solution actually works, look at the brutal real-world benchmarks where this was tested against vision and language models, and then
explore the massive implications this has for the entire field of AI.
You got it, because this is big.
It is big. And what's truly fascinating here isn't merely the fact that this new merging technique works. It's the underlying diagnostic work the researchers did to figure out why previous attempts to merge models failed so spectacularly.
Yeah, they really dug into the autopsy of it.
They did. The core realization of this research is that neural networks are full of noisy parameters that literally cancel each other out when you try to merge them. It forces us to fundamentally rethink what it actually means for a model to learn a concept in the first place.
Okay, but before we can really grasp the brilliance of this breakthrough, we need to set the stage, right? We need to look at the baseline reality of modern AI development so that we understand the walls we're currently running into.
The status quo.
Yeah, let's talk about the engine of the current AI boom, transfer learning.
Right, so transfer learning changed everything. I mean, before this paradigm, if you wanted an AI to classify legal documents, you had to gather hundreds of thousands of legal documents and train a model completely from scratch.
Which takes forever and costs a fortune.
Exactly.
Yeah.
But the pipeline today is drastically different. You start by taking a massive pre-trained model, or a PTM.
Like the big foundation models.
Yeah, so if you're working in natural language processing, that might be Google's T5 or an open source Llama model. If you are working in computer vision, it might be a vision transformer, like a VIT.
Right.
And these models have already consumed vast swaths of the internet or seen millions of images. They possess this broad, robust, general understanding of the world.
They already know syntax, grammar, shapes, edge detection, all that.
Exactly. But they aren't specialists.
Right. They are the ultimate jacks of all trades, masters of none.
Right. They require direction. So you take that generalist PTM and you fine-tune it on a much smaller, highly specific data set for a downstream task. Let's say answering complex medical questions.
Which works brilliantly, right?
It works so well.
Yeah.
Because the model already understands English, you get incredible performance, much faster convergence, and honestly, you don't need nearly as much training data as you would starting from scratch.
But the downside is that it creates a massive structural problem, which I like to call knowledge silos.
Yes, silos are the perfect word for it.
Because now you have this amazing medical QA model, but it is completely isolated from your other model that you fine-tuned to be really good at translating French.
Right. They cannot share their knowledge.
But they're stuck in their own little lanes. If a user asks a medical question in French, neither model can optimally handle it.
And the traditional alternative to having all these isolated, siloed models is multitask learning.
The brute force approach.
Exactly. You just say, I want one master model that can do it all. So you gather your medical data, your French translation data, your coding data, and whatever else you have, and you train a single model on all of those data sets simultaneously from the ground up.
Which, I mean, sounds like the obvious solution. If we have the data, why not just build the Omni model from the start? Why are we bothering with these silos at all?
Well, connecting this to the bigger picture of resource constraints makes the why very clear. Multitask learning is incredibly, prohibitively expensive for most organizations.
Yeah, compute is not cheap.
It's not just compute, though. First, it requires simultaneous access to all your data sets at the exact same time. And in the real world, that isn't always possible due to privacy restrictions, shifting licensing agreements, or honestly, simply because data comes in at different times.
Oh, that makes sense. You might acquire the medical data set in January and the French data set in June.
And if you want a multitask model in June, you have to retrain the whole thing from scratch, passing the medical data through all over again alongside the French data.
Oh, wow. Yeah, the compute cost to train a massive model from scratch on mixed data every time you add a task is astronomical.
It's unfeasible. But beyond the financial costs, there's a massive engineering hurdle. Mixing data perfectly is essentially a dark art.
What do you mean by that?
Well, if you put too much coding data and not enough medical data into the batch during training, the gradients the math pushing the model to learn will pull too hard toward coding.
Oh, so one task can literally ruin the performance of another task while they're training together.
Yes. It requires endless, highly expensive hyperparameter tuning just to get the balance right so the tasks don't cannibalize each other.
Okay, so multitask learning is a logistical and financial nightmare reserved for only the biggest tech giants. And having dozens of fine-tuned siloed models is a deployment nightmare for your DevOps team.
We are definitely caught between a rock and a hard place.
And that friction is exactly where the concept of model merging has emerged over the last few years as the holy grail.
Right. Model merging proposes a tantalizing shortcut. What if we could take those siloed, fine-tuned models, which are cheap, fast, and easy to make independently, and just combine their knowledge into a single multitask model after the fact?
No massive retraining required.
Exactly. No managing complex data mixtures. Just pure math.
Okay, so the specific mathematical vehicle for doing this is something called a task vector. We really need to explain this clearly because it is foundational to the rest of the deep dive.
It is the core building block, yeah.
I like to think of a task vector like a diff file in software engineering. Like when you make a commit in Git, you don't save a whole new copy of the entire code base.
No, that would be terribly inefficient.
Right. You only save the specific lines of code that you added or deleted.
That is the perfect way to visualize it. Mathematically, it operates on the exact same principle. Let's denote the pre-trained initialization, the billions of numbers making up your base model as theta init.
Okay, theta init. Got it.
And let's call the newly fine-tuned parameters theta init. The task vector, denoted as tau, is simply theta if init minus theta init.
Wait, so it's literally just a subtraction?
Just a massive subtraction.
Right.
By subtracting the base model's weights from the fine-tuned model's weights, what remains is a vector that represents only the specific changes, the specific delta, that the model learned to accomplish that one exact task.
It isolates the newly acquired knowledge from the general foundational knowledge.
Exactly.
Okay, so if I have a 10 gigabyte base model and a 10 gigabyte fine-tuned medical model, the task vector is just the mathematical difference between those two massive matrices.
Correct.
So I have my medical task vector, and let's say I do the same thing for my French translation model to get my French task vector. Here is where I have to push back on the complexity of this field.
Oh, here we go.
Well, I mean, if we have these beautifully isolated task vectors, why can't we just smash them together, like pouring different colored paints into a bucket to get a superset of colors?
It sounds so simple when you say it like that.
Right. Why can't we just take the medical vector, add it to the French vector, average the numbers, and slap it back onto the base model?
Because unlike paint, parameter space is highly sensitive to interference. What you are describing is a naive method called simple averaging, and researchers have absolutely tried it.
I assume it didn't go well.
Not at all. And they have also tried significantly more complex versions to avoid the pitfalls of simple averaging. There's task arithmetic, which attempts to just add the vectors together with a scaling factor. There's regmean, which is a much heavier approach.
Wait, let me guess. Regmean sounds like a regression. Is it trying to map the outputs of one model to another?
Close. It stands for regularized mean. It attempts to match the linear representations of the models. It actually requires you to compute inner product matrices of the model's activations based on the training data, and then it uses those matrices to find a closed-form solution to merge the weights.
Yikes, that sounds computationally heavy.
It is incredibly heavy. And then there's Fisher merging, which uses something called the Fisher Information Matrix.
Oh boy.
The idea there is to figure out which specific parameters are most important to a given task and give those parameters more weight in the final merge.
Back up a second. Fisher Information Matrix. That sounds like a concept from a 1950s statistics textbook. What is that actually doing in the context of a neural network with billions of parameters?
Well, you are not wrong about the timeline. It absolutely originates from classical statistics. In the context of deep learning, the Fisher Information Matrix essentially measures how sensitive the model's loss is to tiny changes in its parameters.
Okay, so how do you actually measure that? Like, does the model just know?
Well, no, it's actually about taking second-order derivatives.
Whoa, calculus flashback.
Right. You are basically asking the model, if I tweak parameter number 4 million, just a tiny bit, how drastically does my accuracy drop?
Oh, I see.
Yeah, and if the accuracy drops massively, that parameter has high Fisher information, it is critical. If the accuracy barely twitches, the parameter has low Fisher information.
Okay, so Fisher merging tries to be smart. Instead of just blindly averaging the medical model and the French model, it says, let's heavily weight the parameters that are critical for medicine and heavily weight the parameters critical for French and let the unimportant ones average out.
Exactly.
That sounds like a perfect solution. Why aren't we just using that?
2 reasons. First, the memory requirements are apocalyptic.
Apocalyptic, that's a strong word.
It's accurate. To compute the Fisher Information Matrix for a modern large language model, you have to store gradients for billions of parameters, which requires an immense amount of VRAM. It scales terribly.
Ah, right. The hardware bottleneck.
And second, and honestly more importantly, when you actually test these methods, whether it is simple averaging, task arithmetic, regmean, or Fisher merging, they all eventually fail.
Define fail. Do they just not get any better?
They get actively worse. As long as you're only merging maybe 2 tasks, they work decently. You might get a model that is okay at both medicine and French.
Okay, 2 is fine.
But as you add more tasks, 3, 4, 11 tasks, the performance catastrophically drops. The models just fall apart.
Like the wet clay just crumbling.
Exactly. The knowledge is destroyed in the collision. You try to merge 11 capabilities, and the resulting model performs worse than random chance on all 11.
Which directly sets up the central mystery of this viral research. What exactly is destroying the knowledge when we mash these models together?
That was the multi-million-dollar question.
Right. And the researchers didn't just try to build another blind merging tool to throw on the pile. They performed a meticulous autopsy on the failed methods to see why they were failing. They looked at the car crash in slow motion, and they isolated 2 massive sources of interference.
And this diagnostic work is where the paper really shines, because it provides empirical, undeniable proof for things the community only suspected.
Right.
Let's look at culprit number 1. Redundant parameters.
Okay, so when you fine-tune a model, you are updating billions of parameters via gradient descent. The model is exploring this massive mathematical space, trying to minimize its error.
Right.
But what the research shows is that a vast majority of those changes are essentially just noise. They don't actually contribute to the model's new capability.
Let me give you a concrete data point from the research to illustrate how extreme this is. They found that you can take a newly minted task vector and literally delete the bottom 80% of the weight changes.
Wait, 80%. Just throws them out.
Yeah, literally hard resets them to 0. You just look at the absolute magnitude of the changes, take the 80% of parameters that move the least during fine-tuning, and delete them. You only keep the top 20% highest magnitude parameters.
And when they ran that heavily deleted model, what happened?
The performance didn't drop at all. In some cases, removing that 80% actually caused a slight improvement in generalization.
I really want the listener to grasp the weight of that finding. 80% of the movement during fine-tuning is effectively useless.
Just static.
It's just the model jiggling around in parameter space. It is taking unnecessary steps down the mountain that don't actually get it any closer to the valley.
That's a great way to visualize it.
But here is the danger, and why this specific redundancy completely ruins model merging. Let's say we have our medical model, Model A. For a specific parameter, it made a massive, highly influential change. It moved a value from 0 to plus 10. It is part of that crucial 20% for the medical task. But then we try to average it with models B, C, and D, our French, coding, and legal models.
Right.
For those other three models, that exact same parameter might be completely irrelevant. It might just be part of their useless 80% noise, hovering around a value of maybe plus 0.1 or minus 0.2.
And if you use a traditional method like simple averaging, the math is unforgiving. You're taking the highly influential critical value of plus 10 from Model A, adding the noise from the other three models, and dividing by 4.
Wow.
Your plus 10 suddenly becomes a plus 2.5. Yeah. The noise actively dilutes the important value. It shrinks the magnitude of Model A's crucial parameter, effectively erasing its capability. The redundant parameters across all the different models act like a massive anchor, dragging the highly influential parameters back down towards 0.
Drowning our signal in a sea of noisy, irrelevant updates. That is a brilliant way to conceptualize the first failure mode. So we have culprit 1, redundancy. What is culprit 2?
Culprit 2 is sign disagreement, or sign conflict.
Meaning positive and negative.
Exactly. In neural networks, a parameter can change by moving in a positive direction or a negative direction. Now, imagine you are looking at a single parameter across two different task vectors. Model A, the medical model, learned that to minimize its loss, this specific parameter needs to move strongly in a positive direction, let's say plus 5.
Okay, plus 5.
But Model B, the French model, learned that for its task, that exact same parameter needs to move strongly in a negative direction, say minus 5.
The math there is catastrophic. If you use simple averaging and you add a positive 5 to a negative 5, you get 0.
They completely cancel out. The movement required for Model A is erased, and movement required for Model B is erased. The knowledge of both models is completely annihilated just because they disagreed on the direction the parameter needed to travel.
That is mind-blowing, but I have to ask a foundational question here. Does this sign conflict only happen because the tasks are totally different?
What do you mean?
Like, I can intuitively understand why a French translation model and a medical QA model might want to pull the exact same parameter in opposite directions. They are dealing with entirely different syntaxes, different vocabularies, different logical structures. Of course, they are going to fight over the weights.
That's a very logical assumption, and it raises a critical question about the nature of training itself, which the paper actually investigates. And the answer is a resounding, fascinating no.
Wait, really?
Yeah, they looked at a concept popularized a few years ago called model soups.
Model soups?
Yeah, it's a funny name, but it's where you take multiple checkpoints of a model that were fine-tuned on the exact same task using the exact same data set. The only difference between the runs might be a different random seed or a slightly different hyperparameter sweep. They specifically tested this on natural language inference data sets like RTE, MRPC, and WNLI.
Wait. Merging models that are trying to solve the exact same problem with the exact same data.
Yes, and the data point they reveal is shocking. Sign conflict occurs constantly, even when merging checkpoints trained on the exact same task.
Are you kidding?
Not at all. As you increase the number of identically trained models you are merging, the fraction of parameters experiencing sign conflict scales up dramatically. It isn't just different tasks fighting. It is the same task fighting itself.
How is that even geometrically possible? If two identical base models are learning the exact same task from the exact same data, shouldn't they learn the exact same parameter updates? Why would one model say go positive and the other say go negative?
Not in the realm of deep learning. This all comes down to the concept of over-parameterization. These neural networks have billions more parameters than they strictly need to solve the task.
Right, they're huge.
Because of that, the lost landscape, the mathematical terrain the model navigates to find the lowest error is unbelievably complex. Imagine a massive, multidimensional mountain range with thousands of distinct valleys that are all at sea level. Your base model starts at the peak.
Okay, I'm picturing it.
Run A uses its random seed, and gradient descent takes it down the north face of the mountain. Run B uses a slightly different seed and goes down the south face.
They both end up at sea level. They both achieve 99% accuracy on the training data.
Exactly. But because they took different paths, their coordinates are totally different. There isn't just one single path to the right answer. There are millions of different subnetworks and pathways within the model that can yield the same final accuracy. And those different pathways mean different parameters are moving in different, often conflicting directions.
That completely shatters my intuition about how models learn. So even if you are just trying to build a robust ensemble for a single task, sign conflict is quietly sabotaging your merged model in the background.
It is insidious.
So to summarize the massive problem we are facing, previous merging methods fail because we are taking isolated task vectors, mashing them together, and letting 80% redundant noise dilute the important weights, while simultaneously letting conflicting positive and negative signs cancel each other out to zero.
It is a mathematical car crash. We are actively destroying the knowledge we are trying to combine.
Which brings us to the remarkably elegant solution this paper proposes. If we have finally diagnosed exactly what is breaking the models, how do we engineer a scalpel to fix it?
Well, let's talk about the steering wheel they built to avoid the crash.
Yes. So we know we're drowning in redundant noise and destroying our models with conflicting signs. The researchers introduce a brand new, trending technology, a 3-step architecture to merge these models safely. It is called ties merging, TIES.
Right. Trim, elect sign, and merge.
Let's break down these 3 steps clearly, because this is the secret sauce that everyone on developer timelines is talking about right now. Let's start with step 1.
Step 1 is trim. We already established that culprit 1 is redundant parameters dragging the influential weights down. So ties merging simply eliminates them right out of the gate.
Just cuts them out entirely?
Yes. For every single isolated task vector you want to merge, the algorithm looks at the magnitude of the parameter changes. It takes the bottom 80%, the smallest absolute changes, and hard resets them to 0. It throws them away entirely. It only keeps the top 20% influential parameters for each individual task.
Just like that, culprit 1 is dead. We have completely removed the low magnitude noise that was going to dilute our signal later. By turning them to 0, they have no mathematical weight to drag down the average.
Exactly.
That leaves us with only the strongest signals from each model. But what happens when those strong signals disagree? Like the +5 and -5 scenario.
That is what step 2 is for. Step 2 is elect sign day. This is designed to solve culprit 2, the sign conflict. At this point, even though we've trimmed the noise, the remaining top 20% of parameters across our different models might still violently disagree on whether a specific parameter should be positive or negative.
Right. The medical model might have a strong +5, and the coding model might have a strong -4.
So the algorithm holds an election.
I love this concept. How does the voting mechanics actually work in high-dimensional space?
For a single parameter location across all the models you are merging, the algorithm adds up the total magnitude or mass of all the positive shifts. Then it adds up the total magnitude of all the negative shifts. It compares the two total masses.
Okay, so if the sum of the positive weights is 15 and the sum of the negative weights is 8,
the positive side wins. The direction with the most mass wins the election. That becomes the elected sign for that specific parameter in the final merged model.
I want to make sure the listener really grasps the elegance of this, so let me try an analogy.
Go for it.
Let's say we are in a high-stakes corporate board meeting trying to decide the budget for a massive new project. We have representatives from all different departments: medicine, French, coding, legal.
Okay, I see where you're going.
Step 1, trim, is like kicking out all the board members who don't have strong opinions. If you only care a little bit about the budget, your department's proposed change is tiny. You're out of the room. We only keep the executives who are deeply, fiercely passionate about their numbers.
That maps perfectly to isolating the top 20% of magnitude changes.
Then step 2, elect Jane, forces a binding vote on the overall company direction. Do we fundamentally increase the budget or decrease it? We add up the political capital, the magnitude of everyone voting to increase, and we add up the capital of everyone voting to decrease. The side with the most weight wins the overall direction.
Okay.
Let's say the increase side wins. But wait, what about the executives who passionately voted to decrease the budget? If we just average their numbers in, it's going to drag the overall increase down. What do we do with the losers of the election?
That is exactly what step 3 handles. Step 3 is called the disjoint merge. Once the winning sign is elected, in your analogy, the positive increase sign won the election. The algorithm goes back and looks at the individual models. It only averages the parameter values from the specific models that voted for the winning positive sign.
Are you saying it ignores the others?
Completely.
Yeah.
Any model that disagreed, any model that had a negative value for that parameter is excluded from the average. And of course, any model that had a 0 because it was trimmed in step 1 is also excluded.
Wow.
You compute a disjoint mean using only the aligned values. You are isolating the consensus. Finally, this merged task vector is scaled by a hyperparameter factor called lambda and added back to the base pre-trained model.
So to finish my corporate analogy, disjoint merge ensures you only execute the plan using the budgets of the people who agreed with the winning direction. You completely ignore the budgets of the dissenters.
Yep, you leave them out entirely.
You don't let the people who wanted to decrease the budget drag down the average of the people who wanted to increase it. That is ruthlessly efficient.
What is truly remarkable here is the computational elegance of this approach. Let's compare it again to the prior state of the art.
Okay, let's do it.
Fisher merging requires computing the Fisher Information Matrix, storing massive second-order gradients, which blows up your VRAM. Regmean requires computing and transmitting huge inner product matrices of the training data activations, which is incredibly slow and data intensive.
Right, we talked about how heavy those were.
But this 3-step ties method, it uses simple primitive arithmetic, sorting magnitudes, adding sums, and calculating a mean. It is immensely scalable. It doesn't require any extra gradient computation or transmitting massive matrices of activation data.
It is incredibly lightweight, which is exactly what developers trying to deploy these models need. But, a clever corporate analogy and elegant lightweight arithmetic are only great on a whiteboard.
Sure.
If you are a practitioner listening to this right now, you are probably rolling your eyes and thinking, show me the receipts. Does this actually survive brutal, real-world, multimodal benchmarks, or does it fall apart outside the lab?
Oh, the researchers absolutely did not hold back here. They ran a highly rigorous gauntlet. They tested this architecture across different modalities, different model sizes, and entirely different fine-tuning paradigms to ensure it wasn't just a fluke.
Let's lay out the setup for the listener. For vision models, they tested on the VIT base model, which has patch size 32, and the massive VT large model with patch size 14.
Right, standard vision baselines.
And for language models, they used Google's T5 base and T5 large. They tested scenarios where the entire model was fine-tuned, but they also tested something crucial for modern deployment: parameter-efficient fine-tuning, or PEFT. Specifically, they used a PEFT method called IA3 on a massive 3 billion parameter model called T0.
Before we move on, it is worth clarifying PEFT for our audience. Full fine-tuning means updating all 3 billion parameters, which is incredibly expensive. PEFT methods, like IA3, freeze the vast majority of the base model and only inject a tiny number of trainable parameters, often less than 1% of the total model size.
So it's way cheaper to train.
Exactly. In the case of IA3, it scales the inner activations with learned vectors. The fact that they tested ties merging on PEFT is vital, because that is how most developers are actually fine-tuning large models today due to compute limits.
I appreciate that clarification. It proves they are testing this on the actual workflows people use. And the data sets they used to test the merge were incredibly diverse.
They really pushed the limits.
On the vision side, they merged models trained on 8 totally different tasks. We are talking Eurosetter for satellite imagery, GTSRB, which is German traffic signs, SUN 397 for scene categorization, plus data sets for cars, textures, and digits.
Stop and consider the friction there. EuroSA is top-down, highly structured, macro-level satellite geometry. GTSRB is street-level, highly noisy, weather-dependent camera data.
Right, totally different perspectives.
And SUN 397 is seen differentiating the visual aesthetics of an indoor living room from an outdoor park. These models are learning radically different visual features. Merging them without one overriding the other is an immense challenge.
And on the language side, they merged models trained on 11 different tasks for the PET experiments and 7 tasks for the full fine-tuning. This included natural language inference, sentence completion, and question-answering data sites like WikiQA and Winogrand.
They threw the absolute kitchen sink at this algorithm.
So what were the results? Did the 3-step arithmetic hold up?
Ties merging dominated the baselines across the board. Let's look at the hard numbers. For in-domain NLP tasks, meaning evaluating the merged model on the exact task it was built from, ties beat the strongest baseline by 2.3% on average. For in-domain vision tasks, it beat the strongest baseline by 1.7%.
Which might not sound like a massive, earth-shattering number to a layperson, but in the realm of heavily optimized transformer models fighting for every decimal point on established benchmarks, an average absolute gain of 2.3% across multiple complex datasets is a very big deal.
It is a significant leap, but where the architecture truly flexes its muscles is in out-of-domain generalization.
Oh, this is the really interesting part.
Yeah, because one of the main reasons you want a multitask model in the first place is so it can handle weird, unseen data better than a narrow, fragile specialist. A specialist model often overfits it. It memorizes the quirks of its training data and fails when it sees something new. A good multitask model should be robust.
How did they test that?
They took the Merge T5 models and evaluated them on 6 held-out datasets that were absolutely not part of the merge process datasets like Cosmos QA and Social IQA.
Okay, what do those involve?
Cosmos QA requires reading comprehension and common sense reasoning over everyday narratives. For the T5 large model, ties merging improved out-of-domain generalization by a massive 4.4% compared to the strongest baseline.
4.4% out-of-domain improvement just from changing how we do the math to average the vectors. We didn't add more data, we didn't train it longer, we just stopped the signs from fighting each other.
It's all in the geometry.
That is incredible. But what happens when we push it to the absolute limit? We mentioned earlier that previous methods collapse when you add too many tasks. Did they do a stress test?
They did a scaling limit test, and the visual graph of this in the paper is striking. They plotted their performance as they increased the number of merged tasks sequentially from 2 all the way up to 11.
Okay.
Now, to be clear, as you merge up to 11 distinct tasks into a single set of weights, all methods eventually degrade. You are packing an immense amount of distinct knowledge into a fixed, finite parameter space.
Right. Eventually, the clay has to crack.
But the degradation curve for ties merging is remarkably resilient compared to the others. When merging 2 tasks, both ties and task arithmetic have negligible performance loss, while simple averaging immediately drops by 10%.
10% drop with just 2 tasks. That's awful.
It is. But as you move toward the 11 task mark, task arithmetic falls off an absolute cliff. Its accuracy plummets. Ties, however, maintains a much higher normalized accuracy, degrading at a significantly slower and smoother rate.
Okay, I have to play devil's advocate here on behalf of the scrappy developers listening.
I'm ready.
In these laboratory experiments, the researchers presumably had access to a validation data set to perfectly tune their hyperparameters. They could run tests to find exactly the right scaling factor, lambda, or figure out that keeping the top 20% is optimal for that specific batch of models. What if I am a developer with no compute budget for a validation set? What if I just have to merge these things blind in production?
That is a highly relevant practical concern. Some prior methods, like redmean, try to solve the validation-free problem by storing those inner product matrices. But as we discussed, that scales terribly with large models. The paper addresses this blind deployment scenario beautifully.
How so?
They provide what they call a validation-free recipe. Through their extensive PET experiments across 11 datasets, they found a highly stable default configuration. Just blindly set the trim step to keep the top 20% of parameters and blindly set the scaling factor lambda to 1.
Just hard code the parameters and let it rip.
Yes. And when they applied this fixed blind recipe to entirely unseen settings like full fine-tuning on the vision and language models, without doing any hyperparameter tuning at all, it still worked remarkably well.
Really? Even blind?
Yes. For the VT base model without a validation set, ties improved performance by 6.6% over other validation-free methods. In fact, even with these blind fixed settings, ties merging still managed to outperform heavily tuned baselines like task arithmetic that did have access to a validation set.
That is the definition of a robust architecture. You don't need a massive compute cluster to tune this. You can literally just run the Python script with the default settings and beat the prior state of the art.
Exactly.
But knowing that this architecture wins benchmarks is only half the story. It is great for your GitHub repo, but the ablation studies in this research reveal a profound, almost philosophical insight about how neural networks actually learn.
For our listeners who might be newer to reading research papers, an ablation study is where researchers systematically remove or disable parts of their proposed system one by one to see which parts are actually doing the heavy lifting.
Right, taking it apart piece by piece.
Yeah. If you remove a piece and the performance doesn't change, that piece was useless. If you remove it and the system crashes, You know it is structurally vital.
So what happened when they dismantled the ties merging engine piece by piece?
Every single step proved critical, which validates the three-step design. If you remove the trim step and let the 80% noise back in, performance drops. If you remove the elect sign step and just let the positives and negatives average out blindly, performance drops.
Makes sense based on what we've discussed.
But the most catastrophic drops occurred when they removed the final scaling factor, or the disjoint merge step. In the PAFT setting, removing the disjoint merge, meaning they allowed the losing dissenting signs to be included in the final average, caused a massive 3.2% drop.
Wow, so including the losers really hurts it.
It does. And removing the final scaling caused a 5.2% drop. It proves definitively that taking the mean of all values, including the zeros and the dissenters, actively harms the integration of knowledge.
But the truly mind-bending part of this paper comes from a different experiment they ran regarding the parameter signs, the positive or negative directions. They wanted to see just how important direction was compared to magnitude.
Oh, this is my favorite part of the paper.
Same here. So they took a merged model and they systematically flipped the signs of certain parameters. They literally just multiplied the weights by -1.
This specific experiment is where we see the absolute primacy of direction in neural network optimization. When they randomly flip the signs of the top 20% of parameters, the highly influential ones they keep during the trim step, the model's performance instantly plummeted to zero.
Zero. Just totally broke it.
It completely, totally destroyed the model's capabilities.
Which intuitively makes sense. You took the most important mathematical movements the model learned and you reversed them. You told the model to walk backward instead of forward.
But then they ran the baseline comparison. They left the top 20% alone, and they randomly flipped the signs of the bottom 80% of parameters.
The redundant noise that ties throws away.
Exactly. And what happened when they reversed the direction of 80% of the model's updates? Nothing. The performance barely twitched.
I am still struggling to process that. You reversed 80% of the mathematical updates the model made during training, and it didn't care.
Didn't care at all.
It is definitive proof that 80% of the model's fine-tuning is just wandering aimlessly. It literally does not matter if those parameters go left or right. It is all just statistical static.
It really is.
But that realization sets the stage for the ultimate experiment of the paper, the oracle sign revelation. When I read this part, my jaw actually dropped.
It is an incredibly clever, beautifully designed experiment. We know that step 2 of ties merging the election is fundamentally an estimation. It tries to guess the correct sign for a parameter by holding a vote among the isolated task vectors.
Right. It's a best guess based on mass.
But the researchers asked a theoretical question. What if we didn't have to guess? What if we knew the absolute perfect answer for what the sign should be?
How could they possibly know the perfect answer without training a perfect model?
They couldn't. So they spent the money and the compute to do exactly that. They trained a real, massively expensive multitask model simultaneously on all 11 datasets. They did it the hard way, the gold standard.
Okay, so they have the omni model, the ground truth.
Then they performed an extraction. They looked at the task vector for that perfect multitask model, and they extracted only the signs. Just a massive binary array of pluses and minuses. They discarded all the specific floating point magnitudes.
Just keeping the directions.
Exactly. They call this the oracle sign. Finally, they went back to their cheap, fast ties merging algorithm operating on the cheap, isolated models. But instead of running step 2, instead of holding an election to guess the sign, they just fed the algorithm the exact oracle signs.
Oh, wow.
They forced the merged model to adopt the discrete directions of the perfect model while still using the arithmetic magnitudes averaged from the cheap, isolated models.
I want to make sure I'm following this perfectly. They took the magnitudes, the how far to step from the cheap, flawed models. But they took the direction, the which way to step from the perfect, expensive model.
Yes.
And what was the result?
The resulting merged model achieved a 72.0% accuracy on the benchmarks. For context, the true, massively expensive multitask model achieved 73.1%.
That's practically identical.
It is. By simply supplying the correct directions, just a binary vector of +1s and -1s, the cheap merging algorithm practically closed the gap with the state-of-the-art multitask model.
Let me synthesize why this is such a massive paradigm shift. We have spent the last decade in machine learning utterly obsessed with ultra-precise floating point arithmetic.
Oh, absolutely. FP16, FP8,
FP16.
FP16.
Exactly. We have hardware companies building entire chips dedicated to calculating these matrices, trying to get the exact magnitude of the weights perfect down to the decimal place. But this Oracle experiment completely subverts that. It proves that we don't necessarily need perfect floating point values to merge knowledge perfectly. We just need to know the direction the parameter should move. Is it positive or is it negative?
You are interpreting the implications perfectly. It takes a wildly complex continuous mathematics problem, calculating precise magnitudes across billions of dimensions, and turns it into a much simpler discrete choice problem. A binary choice.
Up or down.
If you get the sign right for the top 20% of parameters, the actual magnitude matters significantly less. The knowledge is not strictly encoded in the specific numbers, it is encoded in the geometry of the direction.
So, bringing this back to reality, what does this all mean for you, the listener? Why should a developer, a DevOps engineer, or a researcher care about this specific finding regarding geometry and signs?
Well, there are huge practical takeaways.
First, on a highly practical level, it means vastly better initializations. The paper demonstrates that if you use ties to merge models trained on 7 different GLUE tasks, which is a standard natural language benchmark, that resulting merged model is a vastly superior starting point for fine-tuning on an 8th entirely new task compared to just using a vanilla pre-trained model.
It's a massive head start.
It creates a robust, generalized foundation almost for free, saving you massive amounts of training time on future projects.
And second, looking slightly further ahead, it opens up radical, highly disruptive possibilities for edge computing and model distribution. If the precise magnitude matters less than the sign, and 80% of the parameters don't matter at all, we're looking at unprecedented levels of compression for task-specific knowledge.
Which is the perfect narrative pivot to our final segment of the deep dive. This is where we transition from the peer-reviewed data into speculation. Just a quick disclaimer for our listeners, everything in the segment is purely for entertainment purposes, only as we speculate on the wild futures of AI based on this paper. I like to call this segment Novel Notions.
I am ready. Where do you see this architecture leading us?
Novel notion number 1, the weightless vector marketplace.
Ooh, catchy.
Right now, if I build an amazing, state-of-the-art, fine-tuned model for analyzing highly complex legal contracts and I want to open source it to the community, I have to upload a multi-gigabyte file to a hub like Hugging Face.
Yeah, and it takes forever.
And if you want to use it on your machine, you have to download that massive file and host it. It is heavy, it requires high bandwidth, and it is inefficient. But based on the Oracle sign revelation, what if we completely stop trading models and start trading signed vectors?
I see where you're taking this. Because the research proves the bottom 80% is redundant, and the exact magnitude of the top 20% matters significantly less than the sign.
Exactly. Theoretically, you could compress a massive fine-tuned update down to a microscopic binary string. Instead of sending billions of 16-bit floating point numbers, I just send a list of +1s and -1s for the top 20% of parameters and zeros for the rest. We are talking about stripping away all the floating point bloat and shrinking a multi-gigabyte update down to mere megabytes or even kilobytes.
The technical grounding there is highly plausible. If the base pre-trained model acts as a shared anchor, meaning both you and I already have the exact same base llama model downloaded on our machines, the delta, the actual new knowledge, can just be the directional vote.
Right. So imagine an entirely new decentralized internet protocol for AI. Your phone or any edge device already has a base model hard-coded into its silicon. Millions of users around the world are locally fine-tuning their models on their specific data, maybe their emails, their coding habits, their calendar.
Federated learning on steroids.
Yes. Instead of uploading massive models to a central server, their phones just broadcast these microscopic, kilobyte-sized direction votes to a global peer-to-peer ledger. Your phone downloads these +1 and -1 votes from a million users, runs the ties merging election protocol locally on the fly in seconds, and instantly merges a hyper-capable, globally crowdsourced multitask model.
Zero central training compute.
No massive data centers, just a peer-to-peer voting system for neural network parameters. I give this a high probability of happening for specialized edge AI within the next 3 years.
That is a highly compelling scenario. It perfectly leverages the discrete, arithmetic nature of the election step. It turns model training into a distributed consensus mechanism. Now, let me pitch novel notion number 2. It's a slightly darker, I call it, forensic checkpoint autopsies via sign conflict.
Oh, I love the sound of that. Cyber forensics and parameter space. How does it work?
We discussed earlier how cybersecurity in AI is rapidly becoming a nightmare. Poison models are a highly credible threat. This is where a bad actor takes a popular open source model, secretly fine-tunes it on malicious data to create a hidden backdoor, and uploads it, hoping developers will use it in production.
And finding that backdoor in a matrix of billions of parameters is currently like finding a needle in a haystack.
Because the poison model still performs perfectly on normal benchmarks. If you test its coding ability, it writes great code. It only acts maliciously, maybe outputting a specific vulnerability when it is triggered by a secret prompt. So traditional benchmarking can't catch it.
Right, you'd never know it was there.
Precisely. But let's look at the technical grounding from the TIES paper regarding the model soups experiment. They proved that models trained on the same task with the same data have a baseline level of sign conflict due to the complex loss landscape.
There is a normal, statistically expected amount of variance.
Right. So imagine a cybersecurity firm using this exact TIES merging architecture, not to build a better model, but as a diagnostic tool.
Using the math of interference to detect anomalies.
An auditor takes the suspected poison model and attempts to merge it with a verified, mathematically clean model trained on the same task. If the suspected model was secretly trained on a radically different malicious dataset to inject a backdoor, its parameter updates its task vector will be moving in entirely different directions to accommodate that hidden knowledge.
The signs will conflict far more than the baseline.
Yes. When the diagnostic tool runs the elect sign step, there would be a massive, statistically anomalous spike in sign conflict at specific targeted parameter layers. It wouldn't look anything like the normal variance of model soups. It would act like a stark forensic fingerprint.
So it flags the model automatically.
The algorithm would instantly flag the presence of a backdoor by analyzing the geometric interference between the models, without the auditor ever needing to look at the massive training dataset or guess the secret trigger prompt.
You are using the catastrophic interference, the car crash we started this episode talking about, as a metal detector. That is brilliant. I would give that a medium probability of becoming an enterprise product, mostly because it is highly non-obvious to current security researchers who are currently hyper-focused on data sanitization rather than parameter space geometry.
But it is perfectly grounded in the physics of this paper.
It all fundamentally comes back to how these parameters interact geometrically. This has been an incredibly dense, highly technical journey today. We started with the sheer DevOps headache of hosting dozens of isolated, siloed models just to get multitask performance.
Covered a lot of ground.
We looked at the failed history of transfer learning aggregation. We saw exactly how simple averaging actively destroys knowledge by drowning it in 80% redundant noise and canceling it out with conflicting opposing signs.
The dual culprits.
And we explored how the elegant three-step arithmetic of trim, elect sign, and disjoint merge solves the problem, pushing the boundaries of in-domain accuracy and out-of-domain generalization without needing a massive supercomputer to compute Fisher Information Matrices.
And perhaps most importantly for the long-term trajectory of the field, we learned that in the vast, high-dimensional space of a neural network, knowing which way to step is far more important than knowing exactly how far to step.
Which leaves us with one final provocative thought. I'll hand it over to you to close us out.
If 80% of a model's parameters during fine-tuning are just redundant noise, aimlessly wandering the lost landscape, and the other highly influential 20% only really need to know whether to vote up or down, are massive trillion-parameter neural networks actually just giant, highly inefficient voting machines? And if so, how much smaller, faster, and cheaper could we make the future of artificial intelligence if we stopped trying to train highly precise floating point numbers and started exclusively training signs? The geometry of intelligence might be far simpler than we ever assumed.
Something for all of you to mull over as you look at your own deployment pipelines. Thank you for joining us on Talk Tensors. The link to the original TIES merging research is in the description if you want to explore the math, the ablation studies, and the benchmarks on your own. Until next time, keep learning.